And essentially, these are the topics that you need to master in these first two chapters. How to interpret measurements. I'm running out of marker here. I may have mentioned this last week, but in chemistry we use the SI system. And the basic 4 units of measurement in the SI system, this stands for International System of Units. It's in French, so that's why it's SI, not IS. Are the meter, abbreviated M, lowercase m. The basic SI unit of volume is the liter, abbreviated capital L. The gram, lowercase g. And then when it comes to temperature, there's still a debate as to whether or not it should be the degree Celsius sometimes called centigrade, or the Kelvin, abbreviated capital K. So that's one of the things that we're going to review in these chapters 1 and 2. The second thing is something called significant digits or figures. In measured numbers. And let me emphasize the word measured. So we'll cover that briefly in a few minutes. The third topic is how to write large and small numbers. So we call it scientific notation, and it's used for representing very, very large and very, very small numbers. And then perhaps the most useful of all the topics, even though artificial intelligence is now out in full force and everybody's beginning to learn how to use AI, things like ChatGPT, we still need to know how to do dimensional analysis. So it's called conversion, factors. But I also have the term dimensional analysis. And that's about the whole 2 chapters, the first 2 chapters. So as chemists, you need to know that not only you measure numbers, but you measure numbers to a certain precision, to a certain degree of accuracy also. Accuracy and precision are slightly different terms, but it doesn't matter what the difference is, because as long as you understand what significant digits are, you are in a good position. So that's what we're going to cover today, and then we'll jump to the lab to see what that lab is all about. Any questions about the topics that we're talking about? Okay. So let me start by very quickly reviewing something that we may have done last week, and that is I'm going to write down here a measurement, and just for simplicity's sake, I'm going to use the scales that are available. And what should I weigh? Okay, I'm going to weigh this bottle of sanitizing liquid. So this lab has these scales, these balances. They're used for measuring mass, weight, if you will. And this one is already on. I'm going to use this one. There's a readout, and you're welcome to come and check it out before you leave the lab, but it's just a readout, a digital screen. And it said 000 to begin with. But now it says 129.667. Now that's the number on that readout. At the very end of the readout, there's a little g. So that tells me that the units that scale, that balance is using for measuring are grams. So you always have to have a measurement with some units. Without the units, the number is meaningless. It means absolutely zero. Nothing. So that G tells me that's a mass. But importantly here, you can tell that the number has a total of 6 digits. 1, 2, 3, 4, 5, 6 numbers. 6 figures. Now, when we talk about significant digits, that word, in fact, is very meaningful. It's very significant. It means that all of these numbers in this measured number are important. You cannot ignore any of them. They were measured to that degree of precision. Now, when I went back to the scale to remove the bottle, this 7 actually was an 8. So first I saw a 7, then I saw an 8. If I go back again and weigh it, it may go back to a 7. What's my point with that? Well, although that number is still considered significant because it's part of the measured number, the very last number in any measured number is a guess. It's always an estimation. There's only one guess in every measured number, and that's the last digit to the right. So this 7, some of you may actually write it as an 8. Some of you may actually write it as a 9, either because the screen was fluctuating, or because if you were using a ruler, that's what you are saying. I'm guessing that this last digit is that. Nevertheless, it's significant. So the number of significant digits on this number is 6. So this number has 6 sig figs. Now there's a problem, however, because if I take something that is very light, I don't know, maybe this cork will work. Right now the scale is at 0, 0, 0. If I put that there, it wasn't light enough, but I'm going to pretend that it was. The scale told me that that cork has a mass of 0.0523. That's the readout. That's what it shows up on the scale. So when the numbers on any measured number are not 0, when they are any other number but 0, they're all significant. But when you have zeros, there's like 3 real rules that you have to remember. In this case, and I'm going to first tell you how many significant digits there are, there's only 3 significant digits. the 5, the 2, and the 3. So this guy has 3 sig figs. Why are the zeros not significant? Because they're only there to tell me how small the number is. They're placeholders. Maybe that doesn't make sense entirely right now, but let me give you other examples. So when you have a small number, less than 1, and you have these zeros to the left of the number, those zeros do not count. They're not significant. What happens if instead of that number, I had this number, 0.0503? So instead of a 2 there, there's a 0 there. This is perhaps the easy rule to remember about zeros. Whenever a 0 is between 2 non-zeros, like a sandwich that inside has 0, the 0 counts, is significant. So this 0 becomes significant because it's surrounded by 2 non-zeros. This number has 3 significant digits. Once again, I'm omitting the units, but I had to put the units there, grams and grams. Now, what if I were to take something, use a different measuring device, and record a number like this, 4,250.2. Well, once again, the 0 is sandwiched between 2 non-zeros. So this number has 1, 2, 3, 4, 5 significant digits. That one should be easy to remember. But what if I write it like this? And I'm going to compare it to this other number. These rules are easier to remember by solving problems rather than by me telling you a name of the rule. But I'm going to tell you that in those two numbers, the top number has 4 significant digits. The bottom number has 3 significant digits. How come? Well, there was no need for me to put that decimal place there unless I had measured that to that degree of accuracy. So that period is telling me I took the trouble to measure to that degree of accuracy, therefore that 0 is significant. But here, there's no decimal place. Now, face it, that 0, it is still a guess, but it doesn't count as a significant digit unless there's a decimal place in front of it. So what's the rule? Well, let me put another number and see if we can come up with a rule. In that number, there's no decimal place. There's only 3 significant digits. All of those zeros are just telling me that the number is very big. The measurement was made to this degree of accuracy, to this 5. The others are just there to tell me how big it is. So those zeros are not significant. Just as these placeholders were there, the same applies to a small number, 0.000000021. Let's call these meters. Let's call these grams. These zeros in front of the 3 are not significant because they're just telling you that this is a very small number. And they're telling you the size, but it's a small number.
So both of those will just be 3 significant.
So this number would have 1, 2, 3 significant digits. This number would have 1, 2, 3 significant digits. Those zeros don't count unless I put a period. If I put a decimal place, all of those zeros become significant. See, that's the trickiest one. That's the difficult one to sort of. Now, sometimes it's not just enough to know how many significant digits you have, but also how many significant digits to report, to write down as part of a measurement. And let me give you this example. Hopefully it will make sense. So I have a rectangle here. And if I did this last week, I apologize, but I think I need to make it clear to everyone else in the class. So this rectangle, let's say that I hypothetically, imaginary, I use a ruler to measure the height, this distance, and I measure that to be, I don't know, 3.92 centimeters. That's my measurement. With whatever device I used, I got that degree of accuracy. I lose that device. I don't have it with me anymore. I start looking for another ruler to measure length, and I find one that is less precise. That one I use to measure this length, and that one gives me a number like 6.3, also centimeters. But it doesn't have the degree of accuracy that this other ruler had. Two different measuring devices, right? One with more precision. Well, that's fine. That number has 2 significant digits. This number has 3 significant digits. Now let's say that I want to calculate the area of that rectangle. And don't worry, you don't have to remember these things, but the area of a rectangle is calculated by multiplying those two numbers. So the area is going to be equal to 6.3 centimeters multiplied by, parentheses indicate multiplication. I can put the little multiplication sign there, but I don't need it. And then 3.92 centimeters. So that's how you calculate the area of that rectangle. Now, if I open a new tab and I just type those two numbers, the beauty of these browsers now is that they understand plain old language and open a calculator, but that's where their ability to do things ends. So just by putting that, the computer is telling me, oh, that's your answer, 24.696. It doesn't help me much more than that, but let me put that number here. So 24.696. What that calculator doesn't tell me is the units. In any measured number, when you multiply units of the same kind, if you multiply only twice, you have to report them as a square. If there were 3 centimeters being multiplied, that would be cubed. If there were 4, that would be to the 4th power. That's something that you had to remember from any arithmetic or math course that you had taken before. But the important thing right now is this number. Is that okay to report as the area? It is not, because it's misleading. It's giving me more precision than my more precise tool. More importantly, it's giving me way more precision than my least precise tool. So when I report this area, I need to be mindful of the number that was the least precise number, because that limits how certain I can be of this answer. And that means you need to look at the number that has the fewest significant digits, 2 versus 3, and round this number to 2 significant digits, to the number with the least number of significant digits. So how do we do that? How do we make this number have only 2 significant digits? Well, the numbers that we're always going to keep are always towards the left. We need to keep that number. We need to keep this number. We need to get rid of those numbers. Here comes the next thing that you need to remember or learn. This number right here is the first one that we're going to drop from the ones we're going to keep. That tells me what to do with this number that I'm keeping, the 4. If this number is between 1 and 4, this number remains that dimension. It remains a 4 in this case. But if this number is 5 through 9, this number has to be increased by 1. That's called rounding up. So what happens in this case? This is a 6. This tells me that I need to increase that by 1. The answer, properly written, would be 25. I can put the decimal place as long as I don't put anything after that, and then say square centimeters. I cannot write 24.7 because that's more precise than this measurement. And I'm limited by the least precise number. That applies to any time that you multiply or divide numbers. When you add or subtract, there's a slightly different rule, but we'll get to that when we see a problem facing that. Right now, what I want you to know is how to reduce numbers to a certain number of significant digits based on the least precise number. Okay, now before we leave this topic and talk about scientific notation, there's two more things that I want you to be aware of. One is the following. So let me see if I can do it right. 3,257,000. So that's 3,257,000, right? Let's call these meters also. And this is a hypothetical question, but it's going to show you something important. What if I needed to reduce these? So, well, first of all, how many significant digits? 1, 2, 3, 4. Those zeros, there's no decimal point, they don't count. So 4 significant digits. What if I were to ask you to write that same number, but only using 2 sig figs? Never mind the reason. Just let's do the exercise. How do we write that to 2 significant digits? We need to drop that, and keep only those 2 numbers, right? And theoretically, these numbers should tell me what to do with that number. So let's do it. 3, this 2 becomes a 3 because of this 5, and the rest I drop. Am I done? No. Why is that? Well, because this number is millions. This number is 33. It makes no sense. So what I have to do is put placeholder zeros. I need to add zeros so that this number is in the millions. How many zeros? Well, 1, 2, 3, 4, 5 zeros. 1, 2, 3, 4, 5 zeros. Now that makes sense, right? Now, 3,257,000 is about 3,300,000. Now they're in the same dimension. Now, I don't want to spend too much time with scientific notation because I think we did talk about scientific notation last week, right? So suffice to say that when you have a very large number, so this number in reality is like this. I'm not going to put all the zeros. Trust me when I tell you that there's like 20-some zeros there. So writing these huge numbers, which are real numbers, they're not imaginary, they're real, becomes cumbersome if you need to add all of those placeholders. So we do what is called scientific notation. Scientific notation is a way of writing big numbers or small numbers using multiples of 10. If the multiple of 10 is a positive number, that means that the number is huge, very large. In this case, it will have 20-some spaces. If the exponent on the 10 is negative, that's what I meant to say, then the number is very, very small. And that would be equivalent to having something like this, 0.00000, 30-some zeros before I get to the 47. So scientific notation is useful to converting large numbers or small numbers to manageable numbers. And the one thing that I'm going to beg you do is learn how to use your own calculator, whether it's an app on a phone, an application on a laptop, an internet calculator, or a real old-fashioned scientific calculator. I thought I saw two here. You need to learn to use that calculator itself. You cannot possibly be non-interested on that because you're going to get the wrong answer if you don't know how to use a calculator. And what I mean by that is that if you need to multiply these two numbers, you better know how to do it in the calculator that you're using, not how I do it here. Essentially, every calculator is different. So the safest part or the safest thing to do is to approach it with parentheses always. This parenthesis is telling the calculator this is one number, not two numbers. A parenthesis here does the same. So we'll have time to practice that in a few minutes. Okay. Now, the one topic that we haven't talked about, and I do want to spend at least 10, 15 minutes on that, is conversion factors. A few minutes I told you that chemistry uses the SI system for measuring length, for instance. So this is SI. In some countries, including the United States, the SI system is not widely used, certainly not in everyday measurements. So how do we measure length in the so-called English system that the US uses? How do you measure length? What units? Inches, I heard. Okay. Is that the only way to measure length?
Centimeters.
Say that again?
Centimeters.
Well, that is not the English system. I'm so glad you mentioned that. So centimeters is still meters. It's part of the SI system, and centi means 1/100th of a meter. So same system with a prefix that changes the dimension, but it's just a matter of zeros, of tens, not a matter of a completely different way of measuring things. How else can you measure in the English system the length of something? Feet. Yard. I'm sure there's another one. Mile. All of that is the English system. If I want to measure something very small in the SI system, I use a prefix to tell me I'm measuring things 100 times smaller than a meter. If I want to measure something large, I use another prefix. This one means 1,000, but it's still the meter. This is just much bigger than a meter, but it's still in the same type of measurement. Here, the relationships between inches, feet, yard, and mile, don't ask me to explain them to you because I don't know how to explain them. I just happen to remember that 1 foot has 12 inches. But I don't know why. How many feet are in 1 yard? Thank you, I didn't know that. So 3 feet in 1 yard. How many yards are in 1 mile? I have no idea. But a lot, right? There's no direct correspondence between these measurements within the same measuring system. So chemists and other scientists decided, you know what, it's a lot easier if we have a measuring system that stays within the same realm of things. It just changes by multiplying or divided by 10. So centimeters divided by 10 twice, kilometers multiplied by 10 3 times, 1,000, 100. So what does that have to do with conversion factors? Well, let's see what the computer says about 1 inch in meters. And miraculously, I get this equality. And I'm going to copy it here because we're going to use it to learn the very basics of conversion factors. So according to that website, and it's accurate enough, 1 inch is equal to 0.054. No, sorry, 0.254 meters. Two things that I had to also mention. When you have a measured number, you know that you have a certain number of significant digits. We just covered that. When you have a counted number, the number of significant digits is infinite. In other words, it doesn't exist. So if I count, these guys are called pipettes. So I just grab 5. If I count them, I have 1, 2, 3, 4, 5 pipettes. I don't have 5.2 pipettes. I don't have 5.05 pipettes. I have 5 pipettes. And I cannot divide them in half. These are units, just like books, just like eggs. Well, eggs you can divide in half, but books you shouldn't be able to divide in half. So whenever you count something instead of measuring something, the number of significant digits is infinite. So 5 pipettes would be written like that, or you can write it like this and add a billion, quadrillion, gazillion zeros. It doesn't have a limit. It's exactly 5. So they don't count when it comes to significant digits. Why am I mentioning that? Well, because the same applies to conversion factors. Conversion factors are considered exact measurements, exact numbers, almost like counted. So the number of significant digits here is infinite. In other words, I'm saying 1.00000 inches equals 0.0254000000 meters. It doesn't matter when you need to reduce a number or increase a number to a certain number of significant digits. Equalities don't count. Now, this tells me that the distance of 1 inch is exactly the same as 0.0254 meters. So if I rewrite this in 2 different ways, I'm going to ask you a question. So if I put this now, instead of as an equality, as a proportion, a ratio, if you will, 1 inch divided by 0.0254 meters. Or I write it over here in the reverse way, 0.0254 meters divided by 1 inch. If I were to ask you to calculate the value of that proportion, of that fraction, what would your answer be? Okay. If I ignore the inch and the meter label, then I can divide 1 by 0.0254 and get a number, right? I can go to the calculator and say, okay, what is 1 divided by 0.0254? And I get that number. Well, that and these are not the same. Why? Because we have the units here. And by putting the units there, I'm basically saying, you know what? 1 inch is exactly the same length as 0.0254 meters. In other words, I'm dividing 3 by 3, or 2 by 2, or 1 by 1. I'm dividing the same amount by the same amount. And what is the answer to that? 1. You don't need to worry about that. You just need to understand that from an equality, if you write the equality as a proportion, you're not changing anything. You're still saying that is equal to that. So that is equal to that. But that becomes very useful, and you'll see why very soon. Same thing for this. If I were to divide that with the meters attached to that with the inches attached, the answer is 1. So now, any equality yields always 2 ratios, 2 fractions, 2 proportions, which we're going to call conversion factors. So these guys are conversion factors. And I hope you see that it's obviously to go between inches and meters, back and forth. However, we can only use one when making a conversion. So how do we use conversion factors if I want to convert a number in inches to meters or a number in meters to inches? Well, let's do it over here. Let's say that I have measured 4.23 meters, and I want to convert that to inches. I want to know how many inches are in 4.23 meters. Well, you start any conversion problems by first putting the information that you have. So you have 4.23 meters. And then you're going to multiply that number. And I'm using the word multiply on purpose by one of these two. You need to choose wisely. Which one do you choose? Well, you choose the one that, when multiplied by that, leaves you with the units that you want, leaves you with inch. And the only one of the two that will yield that is this one, the one that has the inches on the top. You'll see why very soon. So now I'm going to say, okay, I'm going to multiply that by 1 inch divided by 0.0254 meters. And here, now I can use the numbers that are here because I'm keeping the units present, right? Now, something that you had to remember from fractions. This is a fraction except that under here there's a 1, right? So that's divided by 1. In other words, this m, this meter, is in the numerator on the top of this number. This meter over here is in the denominator on the bottom of this second fraction. When you have something like that, it's like having m divided by 1 times inch divided by meter. If we do the fraction operation, that and that cancels each other out because I'm saying meter divided by meter equals 1. Anything divided by itself equals 1, always. So I can just cancel them out, get them out of the picture, and I'm left with inches. That's why this is called dimensional analysis, because we're analyzing the dimension in which we are. So meters cancel each other out, and the only thing left to do is to do the operation that is indicated in these parentheses. And you have to be careful because what we had to do is multiply 4.23 by 1 divided by that. So we're not multiplying this by this. We're really dividing, right? These are fractions. I'm not a math professor, so I kind of suck at trying to explain to you why you do that. But you need to remember your math and realize that, in fact, what we are saying is that this is being divided by that. If that still doesn't make sense, just use parentheses with your calculator, put it like this, and it will do it right for you. Let's do that over here. I don't know how it's going to work in this calculator. Oops, the calculator is here. So I'm going to put what I have over there. I'm going to open a parenthesis, put a 4.23. I'm not going to use the units because I already accounted for the units. I canceled them already out, and I ended up with inches. So that's my first number. And then I'm going to say multiply by, and I don't know if this is going to work, but I'm going to open another parenthesis, and I'm going to put a 1, and then I'm going to put a slash divided by 0.054. 0.0, I always say this number wrong, 254. And I'm going to close the parentheses. I'm trying to make sure that this calculator is not dumb enough to not do it right. Let's find out. So equal. So the answer that I'm getting is 166.5354 etc. inches. Now, is that the right answer? Well, if I were to do it one step at a time, I would say, okay, 4.23 times 1 is 4.23 divided by this. I think it is the right answer. So by using parentheses, I did not make the mistake of multiplying that by that. Let's see what 4.23 times 0.00 is. So now we're going to say, oops, 4.23 times 0.0254. That's a different number, 3.9. That would be the wrong answer because I multiplied this by that, and this not multiplying is dividing by the presence of that line across here. So please be careful, and the only way to be careful is to practice doing problems like this. But anyway, so here we have the answer. Now we are ready to report this as the conversion of this number to inches. Well, our answer is not limited by the conversion factor because this has an unlimited number of significant digits. But it is limited by my measured number. So my answer cannot be that. It cannot be more accurate than what I measured. So I have to reduce this number to 1, 2, 3 significant digits. So I have to get rid of that, that, and that. This is a 5. So this is going to be increased by 1. And my answer at the end of the problem is 167 inches. And that's it. Now that's how you use conversion factors regardless of what you're converting. You start with an equality, you create 2 conversion factors, you choose the one that you need. Okay, so with that, let's open the homework and take a look at some of the problems that you may encounter. And I'm going to go to chapter 2. Please do stop me if you have questions. So this homework is not due until the 23rd of February. So there's plenty of time for you to work on it so that you feel comfortable. And I'm going to open the first problem. We're going to use our time wisely, so I'm not going to answer questions that I think you can figure out on your own. Okay, that I can ignore. Okay, so I'm going to ask you to please do this conversion on your own, using the numbers here, not the ones that you have on your own problem. Because I want to make sure that almost everybody, if not everybody, gets the same answer. Now, we're going to convert centimeters to inches, and I'm going to give you the conversion factor. So I'm going to say 1 inch is how many centimeters. And that's the conversion factor you're going to use. The equality. You're going to start with this. 1 inch equals 2.54 centimeters. Using that equality, please do me a favor and solve that problem. I just want to make sure that everybody's getting it. Okay, are we ready? So that equality gives me two conversion factors, one with inches on top, one with centimeters on top. Which one do I need to use? Do I put here a fraction that has centimeters on the top or inches on the top? Okay, so let's put the two conversion factors here. 1 inch divided by 2.54 centimeters is the same thing. 2.54 centimeters divided by 1 inch is the same thing. I need to choose from those two what to multiply this number by so that I get an answer in centimeters. That's what I want. So which would I choose? Right. So if I choose this one, look what happens. If I put 1 inch and I put 2.54 centimeters, and then I do the dimensional analysis, I look at the units, I have inches on the top, I have inches on the top, that means inches times inches is inches squared. And I have nothing here on the bottom, but I have centimeters on the bottom here. Those would be my units. That's wrong. That's not what I want. I want centimeters. So if I choose what you suggested, if I flip it, and now I do the dimensional analysis, what units do I end up with? Inches on top, inches on the bottom. They cancel each other out. Centimeters on the top, nothing else. I'm left with centimeters. So that was the right choice. You're always going to pick the one with the units that you want at the end on the top. Okay? Now, it's just a matter of doing the arithmetic. 57.0 times 2.54. And we get this answer, 144.78, I think, centimeters. Are we done? Well, let's look at the choices on the problem. And there's no answer like that. There's 145, there's 140, but there's no 144.78. Why? Well, because, yes. Right. So this number has 3 significant digits, right? This tells me that my answer has to be changed to 3 significant digits. So I need to drop that, I need to drop that, I'll keep that, but this 7 tells me that this goes up by 1, so the answer is 145 centimeters. And now, if I look back at the choices, there is one such answer. To remind you, percent means per 100, and is represented by that sign. And it's always the parts of something divided by the grand total of that something times 100. So in this particular problem, we need to figure out what information we have. So we have, the problem is telling us that we have 18% of something. In this case happens to be nickel. 18.0. We know that we have 200 grams with a decimal place at the end of an alloy that contains that percentage of nickel. Now that alloy is called stainless steel. It really doesn't matter, but stainless steel is 18% nickel. If you have 200 grams of stainless steel, how much nickel is in that sample? 36. Say that again? 36 may be the answer, right? So I want to use this formula to figure out the problem. So what I'm going to put here is the information that I have somewhere in this. This 18% is this percentage right here. So 18% equals. Do I have the parts of nickel? No, that's what I want to find out. So these parts, I don't know. Do I have the grand total of the chemical? In this case, the alloy, the stainless steel. Yes, that goes down here. There's a period there. So 3 significant digits times 100. Well, now I have the problem, and now I just have to use algebra. And again, please don't ask me to explain how this is done. I just know how to do it. I hope you remember how to do it. But we need to solve. We need to put these parts on the left side of the equal sign by itself. So I'm going to isolate that and leave it on one side. If this is multiplying here, it's going to come to this side dividing. So I have 18% divided by 100. And if this is dividing, it's going to come to this side multiplying. So that times 200. And that's my way of doing the solving of the equation, the algebra. Again, I suck at explaining math. I'm not very good at that. But I know that I learned that that's how you solve it. So now, if we multiply 200 by 18 and divide by 100, I'm going to simplify it by just going like that and like that. 200 divided by 100 is really 2. And then 2 times 18, 36. That's what you suggested, right? And the units that we're left with are grams. Now the only thing left is the number of significant digits. So there's 3, there's 3. I need to add a 0 here to have 3 significant digits. So 36.0 grams is one of the choices. And that's it. So we have a piece of gold with a mass of 521 grams. The symbol for gold in chemistry is Au. And the mass of this gold nugget is, what was it? 521. Now the problem tells you that you add that to 50 milliliters of water. I need to visualize this question. So I'm going to put my cartoon of a graduate cylinder. So if you've never seen a graduate cylinder, this is a graduate cylinder. Okay? This cylinder has 50 milliliters of water before we do anything. So 10, 20, 30, 40, 50. And there's water there. I'm just visualizing the problem. When I add those 521 grams of gold to the water, the level of the water goes up. So now I drop that. I have this gold at the bottom, and this went up to 77.0 milliliters. The question is, what is the density of gold? Well, what the heck is density? We haven't talked about density, right? In this course, you're going to see that I abbreviate density with a capital D. And I'm going to define it as a simple ratio. This is a really beautiful property of matter. And in fact, is at the end of this chapter 2 discussion. It's always calculated by measuring the mass of a sample and getting the ratio of mass to volume. So how much of a sample in grams occupies a certain space in volume of that same sample size? Most of the time, the units are grams and milliliters. Not always, but most of the time are grams and milliliters. Now, density is intrinsic to a sample. In other words, gold, no matter how much gold you have, is always going to have the same density. It's almost like a social security number of gold. It doesn't change. Now, what's the density, for instance, not in number, but relatively speaking, of feathers compared to lead? So we use the word lighter when in reality we mean less dense. I love the word lighter. I think it's a great choice of words. But lighter implies only mass, right? So we need to think about this in terms of density. So feathers are less dense than lead. So what weighs more, 1 pound of feathers or 1 pound of lead? Same weight. The density may be different, but in mass, and I use pounds instead of kilograms, forgive me. But the density is intrinsic. So feathers are always lighter, unquote, less dense than a metal like lead. So what's the density of gold? Well, we have the information here. We just had to put it on this equation. So D equals. Do we know the mass? Yes, we were given that mass. So we're going to put that on top and the units. Do we know the volume of the piece of gold? Well, we were not even given the shape. You know, we don't know if it's a cube, if it's a cylinder. We just know that it displaced an amount of water when placed on a beaker. I want you to imagine that. Before the gold, this was 50 mLs of water. After the gold, it went up to 77. So the volume of water is still 50. The difference between those two numbers must be the volume of gold. That's how much volume gold has. So yes, indeed, you subtract 50 from 77, and you get the 27.0 milliliter, which is the volume of that sample of gold. So 27.0 milliliters. Milliliters because this cylinder was mentioned in the problem was in milliliters. So let's go back to the calculator and divide 521 by 27.0. I'm just going to put 27 because we're going to do the significant units together. So we have 19.296, blah, 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 blah. How many significant digits do we need to report? 1, 2, 3, 1, 2, 3. So 3 sig figs. What is that number to 3 sig figs? 19.3 grams per milliliter. So let's go back to the problem. And there is a choice. There is a choice that shows exactly that number.